Imagine stepping onto a moon, billions of miles away.
Yeah.
Temperatures just plummeting, total vacuum.
Right. Utterly desolate, you'd think.
Exactly. But what if that seemingly barren surface actually held chemical clues, like vital clues to understanding the building blocks of life? So today, that's what we're doing, a deep dive into this incredible journey with the James Webb Space Telescope, JWST.
Yeah, the JWST findings are really something.
It's uncovering these unique carbon dioxide signature, cohero, on Saturn's mid-sized moons. And our mission isn't just, pointing out, hey, there's cohero. We want to figure out how it got there, where it is.
And what it all means.
Exactly. What it means for planetary formation and, well, the potential for life elsewhere.
And what's really exciting here is that this comes straight from new JWST data. Groundbreaking stuff.
So it's fresh off the digital presses, so to speak.
Pretty much. And we're not just talking about, one simple detection of coheros. The real leap here is distinguishing 4 different kinds. Yeah, 4 distinct types, each one revealed by looking really closely at tiny wavelength shifts in the telescope spectra.
Oh.
And each type tells a totally different story about the complex chemistry happening on these icy worlds.
Okay, so let's unpack this. How did JWST actually manage to sniff out these secrets?
Wow.
I mean, I heard it looked at 8 specific moons: Dione, Enceladus, Hyperion, Iapetus, Mimas, Phoebe, Rhea, and Tethys. That's quite a list.
That's right. 8 mid-sized moons. And the team used JWST's near-infrared spectrograph. NR-spec.
Okay, NR-spec, and that's super sensitive.
Incredibly sensitive. It lets them measure these tiny, tiny shifts in absorption bands right around 4.26 micrometers.
Which is the COA fingerprint.
Exactly. That's where cohero molecules grab light. Their unique signature.
And why these specific moons? Is there something special about them?
Well, yeah. They were chosen deliberately. They have really varied geology, different positions within Saturn's ring system.
Oh, so it's like a natural lab.
Precisely. A natural extraterrestrial laboratory. It lets us compare surface chemistry under really different conditions. Moons right in the E-ring versus ones way out.
Right.
And the precision you need for this, it's just immense, really pushing the limits.
Right. And here's where it gets really interesting. You said 4 types. So what they found wasn't all the same.
Not at all. Very different signatures depending on where they looked.
So let's dive into that first type. What did they find?
Okay, so on the moons closer into Saturn, specifically Dione and Rhea.
Dione and Rhea, got it.
The study suggests the COO is basically deposited directly from Saturn's E-ring.
The E-ring. Remind us what that is again?
It's this diffuse ring, mostly made of tiny ice grains. And those grains are constantly being spewed out by the plumes on Enceladus.
Enceladus, right. The geyser moon.
Exact. Think of Enceladus just feeding this ring continuously.
So what does that direct delivery look like in the data? Is it like a fresh signature?
Yeah, that's a good way to put it.
Because that really changes things, doesn't it? The idea that the rings are actively, painting the moons?
It really does challenge assumptions. What they saw were pretty uniform, narrow spectral lines.
Narrow lines, meaning?
Meaning it fits the profile of fresh cohero molecules just sitting there, embedded in the surface ice. It's strong evidence of this ongoing sculpting by the E-ring.
Wow. Active sculpting. We're only just starting to appreciate that.
Exactly. The full extent is still being figured out.
Okay, so that's the story closing, but you said the chemistry changes as you go further out.
Dramatically. A totally different origin story for the coheros out there.
So what's the second type they found?
Well, further out, you get to Phoebe, Saturn's sort of oddball moon, distant, irregular.
Right, Phoebe.
On Phoebe, the Kyros seems to come from complex organic compounds already on the surface.
Organics. How does that work?
It's a process driven by radiation, like a slow chemical cooking, breaking down these organics. And that process generates Kyros. And then, interestingly, this Kyros seems to migrate inward.
Migrates. It moves between moons.
Yeah, it seems so. It travels inward and ends up darkening patches, especially on Iapetus and Hyperion as it settles onto their surfaces.
Okay, that's complex. How does that Kyros look different in the spectra compared to the fresh E-ring stuff?
Well, the signatures are quite distinct. They show broader, shifted spectral features.
Broad, orange shifted.
Yeah, unlike those sharp, neat lines from the first stuff, these broad signals, they're like fingerprints showing the molecules have been altered, been through some processing.
So it tells you it's not just simple deposition, it's chemistry happening.
Exactly. Dynamic chemical pathways, way beyond just ice landing on a surface.
And then there's a third type. You mentioned something about Kyoros trapped in ice. That sounds really intriguing.
It really is. On Iapetus and Hyperion again, they found Kuro molecules literally stuck inside the water ice itself.
Like inside the ice crystals.
Yeah, occupying tiny microcavities within the crystalline ice lattice. Imagine like a microscopic honeycomb structure, but made of ice, and co-Euro molecules are trapped in the holes.
Whoa.
And this unique situation, this confinement, it leads to very distinct absorption profiles. The way the QO interacts with the ice around it changes its spectral signature. It's recognizable.
That's amazing. It makes you pause, doesn't it? What does that imply about the conditions there? All the micrometeoroid impacts, the temperature changes that could trap gas like that.
It definitely raises big questions about the thermal history, the energy hitting these surfaces, micrometeoroid gardening, as they call it.
Gardening?
Yeah, the constant churning of the surface by small impacts. That could create or rearrange these ice lattices, maybe trapping gases in the process.
So it suggests this really dynamic interplay between temperature impacts, the surface chemistry.
Absolutely. An interplay we're really just starting to figure out.
Okay, so stepping back, what does this all mean for the bigger picture? Are these processes unique to Saturn, or are we seeing hints of something, well, universal?
That's one of the most remarkable parts, actually. There's a striking similarity between some of these CO signatures at Saturn and what we see on Jupiter's big moons.
Jupiter, like Europa, Ganymede.
Europa, Ganymede, Callisto, yeah. Despite, obvious differences in their environments, the similarities hint strongly at universal processes, things happening across the outer solar system.
So we should maybe rethink how we interpret CO on Jupiter's moons, too.
It definitely encourages reevaluation, radiation chemistry, icy surfaces.
Yeah.
There are key factors there, too. Could the same kind of formation and trapping be happening just, in a Jovian context?
And when we talk CO, it's hard not to think. Habitability.
Mm-hmm.
I mean, here on Earth, CO is a tiny fraction of our air, like 0.04%, right?
Mm-hmm.
But seeing it elsewhere, even like this, frozen, it gives clues maybe about past activity, potential biosignatures.
It certainly offers clues. Even if it's not directly life, it tells us about the environment, the chemistry, the energy.
Does understanding these frozen reservoirs on these airless moons give us a new angle for the search for life?
Well, think about Venus and Mars, worlds where COR dominates the atmosphere, drives the climate.
Right, runaway greenhouse effects and all that.
Exactly. So the question becomes, could understanding how COO behaves when it's frozen solid, trapped in ice under intense radiation, could that help us refine our search for habitability markers on, say, exoplanets?
Using these moons as natural labs again.
Precisely. They show us COO under extreme conditions. That's super valuable for interpreting spectra from distant worlds we can barely see.
So what's next? How do we figure out these trapping mechanisms for sure?
Well, the researchers are really pushing for targeted lab experiments.
The lab work? Here on Earth?
Yeah, trying to simulate those conditions. Low temperatures, icy surfaces, hitting them with radiation. Basically, you recreate a tiny patch of Iapetus or Hyperion in the lab.
To match it with the JWST data.
Exactly. Combine that hands-on lab work with JWST's remote view. That should give us a much clearer picture of how the TUA forms, how it moves, how it gets locked into the ice.
It definitely leaves us wanting more. As JWST keeps looking out there, what else might be hiding in Saturn's system?
Who knows?
Could we find totally new chemistry on Titan, or maybe see these organic hero interactions, but deeper inside Enceladus's plumes?
It's entirely possible. The story of Koro on these icy bodies, it feels like we're just on chapter 1.
Yeah.
Every discovery like this, it reshapes how we think about planet formation, how these worlds evolve, and ultimately the potential for life out there. It's this ongoing process of discovery.
What an incredible deep dive today, seriously. From that subtle, fresh Ko delivered by the E-ring onto Dione and Rhea.
Showing the rings aren't just passive things.
Right. Active sculptors, then up to Phoebe, Iapetus, Hyperion, seeing Co-Aero born from organics, moving around.
And then trapped.
And then trapped right inside the ice itself. JWST is just fundamentally changing how we see these supposedly quiet, icy worlds.
It really is. And you should consider how these different CO signatures, found on what we thought were just desolate moons, they might actually be offering the deepest clues. Subtle clues, sure, but clues to the universe's chemical story.
And the conditions needed for life.
Potentially, even on worlds we wrote off as dormant. That makes you wonder, doesn't it? What other hidden processes are happening out there in the cold, dark corners of the solar system, just waiting?
Definitely makes you wonder.
Yeah.
A lot to think about.